Hello everybody, today we will be talking about we will continue talking about dynamic programming. Today we will be talking about dynamic programming on profiles, like and on masks, so like typically to solve NP-complete problems in one way. So the first problem that we consider today is Hamiltonian path. So what it is, you are given a graph. We will be talking about graphs a little bit later, but I will give you an intuition what the graph is. By the way, you already have to know that. So you have a graph. Graph is there is some set of vertices and there is some set of edges that connects two vertices together. And our question is to find the Hamiltonian path. What this path is that you can start at some vertex. And the question is, can you pass all the vertices only once? And at least once. So for example, here we can follow this path, like this vertex, then this vertex, then this, then this, then this, and this is Hamiltonian path because we visit each vertex once, and yeah, because we visit each vertex once. So the problem with that statement is that the problem itself is NP-complete. So what does it mean? It means that it is, as far as I understand, non-deterministic polynomial algorithm. And typically there is a well-known question, P equals to NP. So this guy is polynomial. These are the algorithms that can solve the problem in polynomial time, while these guys can solve in polynomial time if they make the right choices. Typically, that is why it is non-deterministic, since during each step we can ask some oracle to tell what exactly to take. Their idea behind NP is that their answer is typically can be checked in polynomial time. So for example, if we are given a path, we can in polynomial time tell whether it is Hamiltonian path or not. So this NP, so these are polynomial with polynomial complexity. These are with this strange behavior algorithms, but typically there is unknown that these NP problems can be solved in polynomial time. So they're typically solved in exponential. Okay, so how to solve this problem using exponential amount of time? Let us remember what we had last time. We had the dynamic programming on masks. So like we had kind of, we calculate the weight of all the subsets. So consider that we try to have some subset of vertices. Can you come up probably with their solution that solves this task using the dynamic programming on masks or on subsets, as you wish.
Well, we could mask the edges that we traverse. One would be the edge which we passed, and 0 would be which we hadn't passed.
The problem with Hamiltonian path is not about edges, right? It's about vertices.
Well, Well, yes, but I think we need to traverse all the vertices.
Yeah, we have to try, but not all their edges.
Yes. So.
Okay, so what? Yeah, suppose also we have an oracle that tells that special matrix that tells whether V and U are connected. A VU is true if V is connected to U and otherwise. So what you suggest? You suggest to have a mask. So subset of edges.
Yes.
And what will be the state? So the state is subset of edges. Is there anything else in the state?
Well, if you're talking about the state would be the subset of edges that we already passed. And well, the current vertex, maybe something about it.
The current vertex. Okay, good. The current vertex, and then what steps do you want to make?
Then after that we should choose the edge, which would be the next. Well, on each step.
Okay, so we are coming from this state. What other step from it? Then we have some. You mean like that? We have some edge to V, and you have subset of edges together with UV and the V as the parameter. You mean that? Okay. So what do we store in this set? In this dynamic programming, what other answer? Like, what do you store for each state? Like, is it Boolean, or is it integer, or like what?
Well, maybe we could store the number of traversed, but no, we already have this in this state.
Okay, let me see why this solution will, like, it is close to the right solution, but it is a little bit different. That's because suppose you have this edges 1, 2, 3, and you know the set of edges, like the set of edges 1, 2, and 2, 3. And you are right now in the vertex 3. Okay, so you pass this edge and pass this edge. And you can continue adding an edge here, which wasn't here. So you can add, like, from that you kind of will potentially have state 2, 2, 3, 3, 1, 3. Oh, 1. So kind of you. The problem is that, like, and I mean that exactly in this case, this will probably won't work because you will, for example, add only n-1 edges and you stop. But suppose that there is a huge graph that is somewhere here, and you come to 1, 2, then 2, 3, then you don't want to come to 3, 1 again because you already passed vertex 1. How do you check it inside their subset of edges? You just iterate over all the edges and check whether the node is already taken.
Well, I guess we could store, or we could use this, or we could store something else, which would be some set of visited vertices.
Yes. Okay, that's good. So, like, but do we really need the subset of edges? Then, if we store the subset of vertices that we visited, do we need the subset of edges?
Well, in this case, no. But I was trying to think about the masks. So
yeah,
yes.
but you can say subset of V here. So like the subset of vertices that we visited, and the last vertex on the path, on the current path. So, and this will be true or false. Kinda. Can we have a path that visits this number of vertices and ends at U? Then you just can iterate over all the edges and create and check the new subset. Okay, where will be the answer lying? So this DP, where is the answer? How to get the answer whether there is a Hamiltonian path?
And our subset would be all ones.
Okay.
I guess, and if for some vertex it's true, then
yeah, okay. And iterate over all the vertices to check whether we can finish in it. Yeah. An interesting question. For example, we want not Hamiltonian path, but we want to check the Hamiltonian cycle. It's also a P-complete problem because like they kind of similar to each other. What would you add to the state to solve this cycle problem?
maybe we could store something about from where we begin.
Mm-hmm. Yeah, good. We just store here the start vertex as the second parameter. So we will have, instead of 2 parameters at the state, you will have 3 parameters at the state, and then you just again, if it is 1 1 1 1 1 and something like that, then you're fine. Okay, let's write a small pseudocode for that, so that you will be sure that everything is fine. So we come for mask from 0. Oh, sorry, not from 0, because we should start with the masks for which we know there. So our starts will be like that, where this vertex V. So we will start from 1 to 2 in the power of n minus 1. And then for last equal to 0 to n minus 1, if mask and one last equal to 0, then last not in this mask, then we can continue. This check means that the last is really in the subset, so we don't like falsely move from there. Then we iterate for next from 0 to n minus 1, and if mask and one next, one next, yeah, am I right, equals to non-equals to 0, then we say continue. And then if a last next, if there is an edge there, then we can say dp of mask or one next or equal to dp of mask last. This check is not really necessary. We can get rid of it, but like anyways, so we iterate through all the masks, through all the subsets, and we iterate through all their possible last vertex on the path. If, let me do like that, if mask and, like we just can we just can, if not dp mask last, so if the dp says that we cannot find the path from mask to last, then we can just continue with another step. Otherwise, we iterate through all the possible next vertices. We check if this mask doesn't contain this vertex yet, and if there is an edge between the next and last. Then we just can simply say true. Because we already check and we know that dp mask last is true, then all the possibilities that are coming from this state to another state are also true. Does it make sense? So there is nothing really hard in that. What will be the complexity of this algorithm?
It would be 2 to the power of n multiplied by n. I think.
Let's just think a little bit more.
Or and for n also n squared.
Yeah, it's n squared. Okay, great. So if the number of vertices is not very big, so about 20 or so, like we can solve this problem in pretty fast. Do you have an idea on how to change their complexity to this one, where here is n squared is the number of vertices times in the power of 2, and here is the number of edges? Is it clear how to change an algorithm in order to have here m instead of n squared? Yeah, so, yeah, sorry. Probably it will be not trivial because I'm kind of hide from you an important information on how we can store graphs. Because right now we have this oracle that tells us whether there is an edge or not. We also can store the edges in the list of edges. So a special array where each element is an edge. And that's all with the length m. So do you have any ideas on how to do given this array of edges?
Also for each mask.
Yes, for each mask.
We should consider, I guess, all the edges that would extend.
Okay, okay, yeah. We can do like that. We can do for last equals to 0 times n minus 1, and here, for example, coming not only by the next, but for all the edges that are next, last, inside. This is what you meant. This is a little bit different than I mentioned here. So this guy is the edge list. Edge list is just the list of all edges in the graph, and there is this guy was adjacency matrix. And there is also adjacency list. Which means that we have n lists where for each vertex we store exactly the edges that exist out of it. So let us consider what will be the memory complexity of this guy, how much we store on the edge list. Like we have n the number of vertices, and m is the number of edges.
About adjacency list, is it vertices there? Which?
So we have an array of lists.
Okay.
Where for each vertex we have the list of its neighbors. So this one, what is the memory complexity? Yes, it's simple.
So it should be m or?
Yeah, it is m because it's exactly m elements. So okay, adjacency matrix.
It should be n squared.
It should be n squared because like it's the matrix simply, and this guy.
It should be n multiplied by m, maybe. Well.
No, it will be not multiply because you not store for each vertex all the edges, right? You store only the edges that are coming from this vertex.
It should be 2m. Yes.
Yeah, but we're talking about complexity, so more generally it will be O of n plus n in this case, because the array is at least is exactly n, so you have to store n at least.
Okay.
And each edge is considered only once here. So that is why it is n plus m, because sometimes m can be smaller than n, so you want to have a complexity n plus m. So by that you just can for next in edge last. So we iterate through the list of this of neighbors from adjacency list, maintain, and you iterate over all nexts, and then you just of course you should remove this check because you already know that there is an edge. So and that is why you kind of remove their complexity from n squared to m. Is it clear why?
Oh yes, yes.
Yeah, because we iterate over each edge only once. In one direction. You can in both directions, but these two loops they're not squared already, but they're the total number of edges. Okay, great. Whew. So this is Dpm mask. Typically, you should be able to after that you should be able to solve any problems given where you have to understand that the state is some subset. So you will be able to do that. I mean, typically for dynamic programming problems, it's easier to come up with this solution, even that it is not very fast, but at least there is some solution for dynamic programming that you can come up with. But this seems similar to their, how to say, this is similar to the recursive function that goes over all the possible states to fill, but it works faster because in the all possible states there will be n factorial or something like that, while here you get down to 2 in the power of n because you don't care about the order of the prefix of this path. You just care only on the vertices that you already visited. So these solutions make sense. Especially in NP-complete problems. Typically, to give you a little bit of additional information, for NP-complete problems, there typically exists a relaxation of the problem. For example, there is a problem named how to say it? Salesman problem. I think it's named salesman problem, where you have on each On each edge, you have a weight of its edge. It's kind of there is a city of n houses, and there are rods between each city, and each rod costs some weight. You know for each rod what weight it is, and you want to find such a path with minimal weight that traverses over all the vertices. So the first thing that comes to your mind is kind of the best thing. It is a Hamiltonian path of the shortest, or with the shortest sum. But it appears that if you make, for example, the minimum spanning tree on that, and you go like that, so you're not necessarily, you do not imply to visit each vertex once, but like, let's suppose that we can visit each vertex several times. We don't care really about this condition. So this path is only 2 times bigger than this Hamiltonian path. So kind of this is a little bit relaxation of the problem. So you're asked not for the best, but for the best with like 2 times approximation. And there are lots of NP complete problems, NP problems that can be solved. Which relaxations can be solved? So like you give, for example, I don't know. No, I don't really know. The good problem is instead of salesman problem, but kind of in this case you just have an answer that 2 times worse, and sometimes we are fine with that. For example, if you want to find exactly the Hamiltonian path, something like that, there is an interesting, if you have kind of the vertices on a plane, and the weight of an edge is their distance between these 2 points, then there is an interesting algorithm that kind of takes any path, and then like if it intersects somewhere like that, if it intersects, then it's better not to have this pair of rods, but better to have this one. So kind of we change crosses to like the parallel lines, and this appears to give a good approximation for the algorithm. Like I'm just giving you an intuition that there is, for NP problems, you can solve this problem in polynomial time, but get a little worse solution. And it's typical. It's the typical because salesman problem is NP complete problem, but everybody is solving it right now, like in some for the couriers, for example, when they have to deliver something, they create a path that is better for their employee, but it is not 100% okay, but it's approximately good. And there are algorithms for that. Okay. Then let us talk about their Dpm profile. You are given a rectangle n times m, and you want to find, like there are 2 problems really, where you want to find the total number of coverings by the dominoes, like the rectangles of 1 by 2, like the number of ways to fill this rectangle with this 2 times 1 dominoes, or you are given again the table, and some of the cells are thrown away, and you want to check whether you can fill the rest in the dominoes n times m. This problem can be solved in polynomial time, also as is, but this even has like, there is a solution for that problem, which works in M-type SAM. There is a formula for the number of like domino tilings. But for example, if you kind of merge these problems together, if you want, for example, calculate the number of possible ways to fill this rectangle with some closed cells with dominoes, this will already be in the calculator. Like if you want to calculate the number. So let us solve the first problem, just where we calculate the number of tilings. This problem will be solved in a similar manner, but we kind of omit it. We don't need to make it. Why on profile? Why we're talking? Like, let's feel. So we know that n is somewhat small. I don't know, 8, and m is like 1000. I don't care exactly. So you know that one dimension is very small, and another dimension has some reasonable length. Let us try to fill the dominoes line by line. Kind of we fill the first column, then the second column, then the third column, and etc. So what's happening here? We see their empty cell, and we either can put vertically or horizontally. For example, we put horizontally. Then the one we put vertically, then another one put vertically, then horizontally again, and horizontally again. Like, suppose like that. You see that we already filled this first column fully, and you have some of the cells that are taken already by the dominoes on the left. This will be exactly our profile. Our profile will be, so we already filled the first. So we already filled the first I columns, and there are some dominoes that are taking one additional cell somewhere. So for that, we just store here 0, 1, 0, 1, 0, 1. That would be like 1, 1, 0, 1. So this is the profile. Like we know that we filled already all the first I columns, and we know that some cells are already taken by their dominoes on the left, and this is exactly, we don't care about how the dominoes are exactly posing here. We only worry about which cells are already taken to the right. So we have dp, column, and mask. Again, mask will correspond to whether we take the cell or not. Okay. The first dynamic programming profile that we will be talking about is a little bit complicated. We will talk on how to improve it later, but let's start from the first. Suppose we want to, like, the first idea that comes to mind is that we kind of can change the column and calculate the new mask. Okay? So you want to come from this state to dp col +1 with some new mask. Okay, we can pre-calculate for each pair of mask can we come from this mask to this mask? Can we put the dominoes in such a manner that we can come from this mask to this mask, including for example, the number of ways of how we can change from one to one. This can be done in in kind of recursive manner, because you have only kind of their stripe of 2 times n, and you have to fill it with their dominoes. So for example, in this example, there will be 2 different ways how to fill. It is either this one or this one. One moment. Yeah, I think we don't even care. There is all. Luckily for us, there is like if you want to have from mask on the column and on the next mask with mask like this tagged mask on the next column, there is only one way to fill it with dominoes in such a manner that we can get the second mask. There is only one way. So then I'll just...
If you have a square, for example, there should be 2 ways.
Yeah, but as you can see for the square, there are two edges from this mask. So we have mask equals to 0, but you want to do only by 1 column. So if you put like the domino like that, then you will have 0, 0 here. If you put a domino like that, you will have 1, 1 here.
Oh, okay.
So they are a little bit different. So they kind of filled, but here it is zeros. Here it is zeros, and here it is ones, because we move exactly column by column. So the solution is pretty simple then. We just iterate for a column from 0 to n minus 1 for mask from 0 to 2 power of n minus 1. We calculate for mask with their ampersand, like with strike 0 to 2 in the power of 1 minus 1, and if a mask. So we pre-calculate all these edges. So if there is an edge between them, then dp of col plus 1 mask with the stripe plus equal to dp col mask. So we just take each column 1 by 1. Like how many columns did we already process? Yeah, I think it should be like that. How many columns we already processed from left to right? What is their profile there? And we iterate through all the possible pairs with this profile and check if we can go from this mask to this mask. Then we add the answer to that one. I think it's pretty clear what if we have here closed cells. This check will be a little bit more complicated, but we can using the recursion kind of to iterate over all the possible ways to fill the dominoes there. We can get it like in reasonable time. Okay, how to initialize that?
Do you know about A, which we pre-calculate, or the first?
No. Suppose we understand how to pre-calculate this. This can be done using finding all possible ways, like using recursion to fill it 1 by 1. Now, how we should initialize dp? Like at the beginning, how many columns did we process?
No columns.
0, right? Then what is the profile there? At the beginning.
Do you mean we could have the fake column on the left, which would be all ones?
I mean, each time when we calculate Dpm profile, we calculate for their how many columns and what are their already taken cells to the right. So at the beginning, all zeros. Yeah, okay, we know how to initialize. It's dp00 equals to 1. And everything else is equals to 0. Then where lies the answer?
The answer would be
like how many columns have we passed? Here, at the end.
N.
And
M columns, I guess.
And mask the profile.
Well, actually, I thought that yes, the mask would be all ones because we filled the last column.
Okay.
It would
Okay.
be M minus 1.
There are two ways how to calculate. It's either n minus 1 with all ones, or it is dp n 0. Like it's similar things. It's kind of either we processed n columns and there are no taken cells, or we processed n minus 1 columns and all the cells already taken. Okay. So this is how we calculate. Like, can you tell me their approximate complexity of this thing? If we can check in constant time, so this check works in of1.
Oh, it should be n multiplied by the 2 to the power of n. Well, 4 to the power of n.
Yeah, 4 to the power of n. Great. That is why n is so small, typically in this thing, because like it's. However, this is quite complicated. Like, this part of the solution is quite easy, but the part where you check whether you can go from one mask to another mask is a little bit complicated, because you have to do some recursion and you're trying to fill all the possible ways, and it's just a little bit complicated.
Well, actually, I guess there should be an m in the complexity. The first.
Oh, yeah. So it should be m. The number of columns is m. So like, yeah, it should be m times 4 to the power of n. Okay, we know right now that it's pretty complicated to put the whole column. So kind of we have column I, and then we fill in such a manner that we fully filled the column I plus 1. Like, there is a huge step. We put more than one domino there, like some strange amount, we don't know exactly, but not one, maybe more. The next kind of simplification that we think, can we deal with some of dynamic programming on profile in such a manner that we can add only one domino at a time? So we don't have to think about how to change from column to column, but by adding one domino at a time. For that, there is an interesting approach is that it will be with curved profile. Like, profile will be curved, so it will be like that. So it is column I, and there are some cells that we already filled with dominoes here, and kind of everything here is filled with dominoes, And the profile is just whether we have here a domino that is filled here. So instead of column by column, we have like this curved profile with one position, and again we have here 1, 0, 1, I don't know, like 1 here, 0 here, 1, 0 here. And so what's happening here? We can add one domino only at a time because we want from this state move to this state. Like only by changing one cell. So what's happening? If this cell is already taken, consider several cases. So if it is like that, then it is already filled, and there is only step here is to come take this cell here and write here 0, because we cannot put the domino anywhere. Then suppose here is 0 and here is 1. Then there is only one way to put a domino, so we consider we make a step to this state where here is 1, so like there is a domino like that, and some value here. So, and there is the third case where there exists two steps. So it is either, if it is 0, 0, it either can move to the state 1. So here, like again, the domino was like that, put like that, or the domino is put vertical. Then we will move to the state where this were 0, and right now this is 1. Like the domino is placed here. Does it make sense? Or it is complicated?
Well, actually, I missed where are the dominoes in the last cases.
So there are like, if you have two zeros, you can have two options. You either put the horizontally, one domino horizontally. So this you put horizontally. So instead of 0, now there is a 1 here, and this is still 1. Oh, sorry. It is still 0 here. Or you add vertically, and then this both cells becomes 1, and you move to this state where we put this domino vertically, and there is 1 already here because it is covered by this domino right now.
Okay, I get it, but how does the 0 in the on the left of the split, how does it correspond to the actual values in our state? So we have 0 after we made a move. There's a 0. What does it mean?
So our state will be the column, the row, like this cell, and the mask here, and the mask that it is here. Then we want to make steps. So what's happening? We just add row plus 1 column, and the mask is changed correspondingly. So it is either it becomes 1 here, or it is becomes one here. So in this case, here is 0 in the new mask, and here is 1.
Okay.
So there are steps, like only like if it is 1, then there is only a simple step replace 1 with 0, so the new mask will be everything the same but with 0 here. If it was 0 and the next one, then we can only put it horizontally, then the change will be only 1 here for the mask. And in the third case, there can be 2 changes. Either one becomes in this position, or either one become in their second position. And that is how you just recalculate. You just recalculate by adding their answer for this mask to their answer for that. And of course, you have to store something like that. dp column row plus n, dp col n mask equals to dp col plus 1 n, col plus 1 0 mask. So if you if you already pass through all the rows, your profile is like that, it is exactly the same as this profile. Like, that's how we move from one column to another column. Could you tell me the complexity of this algorithm? I will not write the pseudocode. I don't want to. But what is the complexity of this?
So
like how many states? There, let's start with
steps.
States, visited states.
So it will be all rows multiplied by all the columns and all masks.
Okay, so what it is?
So it would be n by m by 2 to the power of n plus 1, I guess.
No, there is exactly n mask. Mask is always of size n. So it's one per row. So it's n times 2 to the power of n. Then for how much costs their step? How much does the step cost?
Well, one step should take iterations through the masks, I guess.
Yeah, iterations through the masks.
And just constant.
Yeah, it's just constant because there are only like at most 2 steps can be there. Then your complexity will be like that because for each state you move only constant number of times. Then the time complexity is this one. So we went from n 4 times n to nm 2 times n, and it becomes even simpler to write. You don't have to come up with this edge array from mask to mask. A little bit simpler. Okay. There is another problem. Similar to that, and it is again solvable by Dpm Profile. You have to calculate the number of ways to color each cell in 2 colors, black or white, in order that there are no all 4 whites and all 4 blacks. These are not allowed. But let's try to let's try to think what is the state here and what is the profile and how we can add. So again, the idea is the same. We store this curved profile and we want to add one edge. Oh, sorry, one cell, one by one. So kind of you want to move from this to this. So what do you think? How it can be solved?
Well, I'm thinking of two options. Whether we make one move, we should check whether we can put a white cell here or a black cell or both of them. So, and
okay, what will be the state right now? What mask will be on which? So it's a little like the mask here is a little bit different. So previously we had mask like for each row once, but now do we need another? Some additional. So when you add this cell, about which cells do you worry about?
About the three cells.
You worry about these three, right?
Yes.
So instead of one per row, we'll have 1, 0, 1, 1, 1, 0. We'll have one more. Our mask will contain one more element. It is the one that is on the corner of this because we care about that. No, and then it's again the same way. You just put here one, and then you check whether it is all ones or zeros, and then you move here, you just replace this with the new one here, and you just come there. So their solution will be almost the same, but the mask is a little bit different. Okay. Let's talk about a little bit more complicated problem. So you have a table n times m with some cells thrown away. And we want to calculate what is the maximal number of rooks we can put on this table in order they don't beat each other. So the rook is from the chess set, the figure that beats horizontally and vertically. So if you will come with a solution, just tell me. If you have.
I'm thinking maybe we could have some mask that says whether for each row on each step whether this row is already covered by some rook.
Yeah. Okay.
Put another rook there somewhere.
Yeah, exactly like that. So I kind of suppose we consider a row. Like you have mask like that, and you know which lines already like under the rook. So it is, I don't know, 1 0, 1 here, and here is 0 0 0 1 0. And then you check till the next thrown away cell. You check how many rooks you can put here. How many possible ways like this? Like there is all the zeros from here. Like you can put only one rook here because this is the vertical line. You can put there only one. So you just choose where to put, and for example, if you put here, then in the next step it will be. It was 0 here, then in the next step it is 1 here. Okay, and for example here, if it was 1 before and now it is thrown away, like let us consider that kind of rooks cannot beat over the thrown away cell. You just get from 1 0 here, and so on. You just go like, but this time their step is a little bit more complicated. It is from one thrown away cell to another thrown away cell. So it's like through. It's not 1 by 1, but it's a little bit bigger as a jump. Can be for the step. Okay. Suppose we take a bishop right now. So the bishop is the guy who beats diagonally. Any ideas? It's already a little bit trickier.
Can't we do the same thing?
We cannot do exactly the same thing, because when you have one here, it is either you don't know in which way it beats. It's either beats from in this direction, or it's either beats in this direction. You don't know. It's either the bishop is somewhere here and it beats like that, or the bishop is somewhere here and it beats like that. You don't know exactly. So like it's a little bit more complicated.
Well, an easy solution would be to store a 0, 1, or 2.
Not exactly. Why 0, 1, and 2? There can be 3 also. Like one cell can be like there is either this bishop, or both. There can be. So it's yeah, you could store here 2 bits instead of 1. You can store either it is from one bishop or it is from the other bishop, and then when you want to add this new cell, you just check whether it is under the bishop from down or from the bishop from top, and then you just say, if not, then we can add a new cell. So it's a little bit complicated, a little bit more complicated, but theoretically it is fine for us to solve using this. Okay, and suppose that right now we have a king. King is the guy who beats the rectangle 303.
Well then, on the next step we only need to know whether there is a king somewhere on the left.
Okay.
Oh, well.
Yeah, it's also a little bit more complicated. But I think you're right. Anyway, the same solution should work. Kind of, you want to understand whether you can put a king in the cell. It can put there if here is zeros and down 0 and on top 0. Then you just do like that and come with another cell where you can be picking. So that's standard, and we are almost finished with dynamic programming. Like, I will give you today some problem, like let us solve it at first, and then like that's it for dynamic programming on Profile for today. So let's solve an interesting problem. You are given a line that consists of A, C, B, that contain only A, C, B's and C's. And you want to calculate the total number of times you can choose 3 indices in their increasing order that they will have A, B, C there. So for example, in this case, there is A, B, C here, A, B, C here, A, B, C here, A, B, C here, A, B, C here. No, again, like there. Here is A, here is B, here is C, and we want to calculate the total number of ways for 3 characters to be A, B, C. Not necessarily consecutive, but with some.
Not necessarily consecutive.
Not necessarily consecutive.
ABCs there.
ABCs, yeah. So for example, this one is the correct triple. They are not consecutive. There is some blanks there, but it's still ABC. ABC there.
I think here we could just iterate over it, and for each, for example, if we are on B, we should store, well, if we would have a second array, maybe we could store the number of A's that were before that B. Then for the next B it would be the same. And for the C, we should sum all the numbers from the previous bits. Something like that.
Yeah, something like that. So for each B, let us calculate the number of ABs. This is exactly the number of A's on the left. Then you know already at each B, you know how many ABs are there. So this is A, this is AB, the number, and for ABC we again calculate the prefix sum. That is correspond to AB, and then you add C. The other way around is, for example, to take B, calculate the number of A's to the left, the number of C's on the right, and multiply it. This is also a possible way, because like this B will be in this number of ABCs. So what will be the complexity of this algorithm?
Well, I think we could do it in 3 multiplied by the length of the sequence.
Then the complexity?
Just n.
Yeah, just n. You don't have to think about their constants. Here you just have to think about their general complexity. Yeah. So if the length is n, then this is all n. Okay. I think that is it with dynamic programming. Any questions up to that point?
No?
Okay, great. Thank you very much for coming. See you next time.